Welcome to the Explainer. Today, we're going to break down a really powerful shortcut for one of the most common puzzles you'll run into in calculus. You know the feeling, right? If you've ever tried to plug a number into a limit and gotten this, it's a confusing moment. It feels like you've just hit a mathematical wall. But here's the thing. In the world of calculus, this isn't an error. Think of it more like a signpost, a little clue that there's a hidden answer just waiting to be found. We just need the right tool for the job. So what does it really mean when we get a result like 0 over 0? Let's dive into this idea of an indeterminate form. Okay, think of it like this. When you get 0 over 0, you've got a function on top that's racing towards 0, and another function on the bottom that's also racing towards 0. The limit, the actual answer, all depends on which one gets there faster. The whole thing is about figuring out the winner of that race. And this picture here? It just visualizes the whole idea of a limit perfectly. See that little open circle at x equals 2? The function isn't technically defined right at that point, but the limit still exists because from both sides, the function is getting closer and closer to a y value of 4. With limits, it's all about the journey, not the destination. So if we can't just plug in the number, how in the world do we solve these 0 over 0 puzzles? Well, let's meet our special tool for the job, LHospitalsRule. Now, I know this is the formal theorem, and with all the notation, it can look a little intimidating. But trust me, the idea behind it is actually surprisingly simple and, honestly, kind of elegant. So here's the crucial point, and you gotta remember this. You are not using the quotient rule. Forget about it. You treat the numerator and the denominator as two totally separate problems. Just take the derivative of the top, then take the derivative of the bottom. Then you see what the limit of that new fraction is. That's it. All right, enough with the theory. Let's actually put this brilliant shortcut to work with an example and see how it all comes to life. So we just followed these 4 simple steps. First, we got to confirm it's an indeterminate form. Yep, 0 over 0. Check. Then differentiate the top, differentiate the bottom, and now let's reevaluate this new limit. Look at that. The sign terms cancel out, leaving us with the limit of 2 times cosine of x as x goes to 0, which gives us our answer, 2. Okay, but what happens if applying the rule once just isn't enough? I mean, sometimes you might do all that work just to find you've landed right back on another indeterminate form. Right, so for this problem, after our first go with the rule, we check the form again. The numerator, 1 minus cosine of 0, that's 0. The denominator, 3 times 0 squared, also 0. We're still at 0 over 0. But hey, no problem. The rule says we can just apply it again. So we differentiate the new top to get sine of x and the new bottom to get 6x. This gives us the limit of sine of x over 6x as x approaches 0. Now, for those of you who remember your fundamental limits, you know that sine of x over x approaches 1. So this limit becomes 1/6. And there we have it. After applying the rule twice, we get our final answer of 1/6. This is a perfect illustration of the power of this rule. You can keep on applying it as many times as you need to, just as long as you keep getting an indeterminate form. Now, you might be thinking this is just a one-trick pony for 0 over 0 problems, but this tool, it's way more versatile than it looks. It turns out LHospitalsRule can also handle all these other indeterminate forms, like infinity over infinity, or even these really unusual ones. The key is to use a little bit of clever algebra to rearrange them into that 0 over 0 or infinity over infinity fraction that we know how to work with. Let me show you how. Take this limit, which has the form 0 times negative infinity. We can't apply the rule directly, but with a neat little algebraic trick, we can rewrite the expression as the natural log of x divided by 1 over x. And just like that, we have a fraction in the form of infinity over infinity, and it's ready for our rule. And once it's in the right format, we just apply the rule like we did before. Differentiate the top to get 1 over x, differentiate the bottom to get negative 1 over x squared, and then we simplify the new expression. What do you know? We find that the limit is 0. It's a fantastic technique for making this rule even more useful. Okay, now before you get too excited and start using this for every single limit problem you see, there's a really crucial warning we need to talk about. You gotta remember, this is a specialized tool, not some magic wand for all limits. If you use it in the wrong situation or when there's a simpler way, you can actually just get yourself stuck. Just look at this example. The limit is infinity over infinity, so it seems like a perfect candidate, right? But when we apply the rule, taking the derivatives,
Well, it just flips the fraction upside down.
And if we apply it a second time, it just flips it right back to where we started. We are completely trapped in an infinite loop and we're not getting any closer to an answer. In this case, the better way forward was just good old-fashioned algebra. By rewriting hyperbolic sine and cosine using their exponential definitions with e to the x, and then dividing everything by that highest power, we can simplify the expression and easily see that the limit, the real answer, is 1. So I guess the key takeaway here is to always analyze the problem first. LHospitalsRule rule is an amazing shortcut, but it's just one tool in your mathematical toolkit. And knowing when to use a tool, well, that's every bit as important as knowing how to use it.